Okay, so I already set the stage. We again solve the same set of equations. By the way, eigenvalue problems are pretty broad. Okay, mathematical methods, you might have done this problems, but here I will keep equations simple, and my solution also simple. Actually, in fact, it's not eigenvector, but it's eigenfunction. So. Okay, eigenfunctions is more appropriate word, though it can also be called eigenvector. Okay, so the statement is the following. So we give the boundary values, but so these are fixed. Now I'm looking for lambda that satisfies this equation. Well, lambda that satisfies these boundary values. Okay, so it has exact solution, right? So my solution is sine root minus root lambda y. Okay, so lambda and this should be for satisfying the boundary condition. It should be at 2, no? So 2 times minus root lambda should be equal to n pi. So lambda n equal to minus n by 2 whole square. Okay, so that is my solution. Okay, so idea here is again use one of the root finders. So iteratively. So what I want to solve is x equal to 2, value of y for given lambda is 0. So find lambda which satisfies this. So you can iterate correct value of lambda. So this is a code. Here I use secant method. Okay. So, by the way, please remember for this problem, any slope is my problem is only lambda. It should be correct lambda, but slope can be arbitrary. So slope I choose. So this is I'm again going to use OD int, and initial value is 0, and initial slope is 0.1. Okay. So my starting point is -2 for a. Okay. By the way, so remember n was a was n pi squared by 2. So my first value is n equal to 1 is pi squared in pi by 2 whole square, no? Pi by 2 whole square. So pi squared by 4. That's the first value. That's what I'm after. First eigenvalue. A second value eigenvalue is pi squared. N equal to 1, n equal to 2. I'll solve for both. We start with -2, and I apply a secant method. So OD int y end is I just look at what is y end for this solution OD int. Okay, and I plot it here. Now I need 2 values. No, for secant method requires 2 values, 2n minus 1, and I iterate it. So if the absolute value of a minus a previous is greater than tolerance, so the 2 adjacent value is less than tolerance, and iteration is less than 10. And apply OD int and plot. And here y. So basically, I'm just looking at the endpoint. So endpoint is 0. It should be 0. But do I go above 0 or below 0? So this is my shooting method. So basically, I'm shooting to that 0 value. And this is my y. So y is 0. Well, basically 2 values, one above and one 0. Or it could be both in the same direction as well. Okay, -2, -1. Okay, so it could be any direction. So this and secant method, no? So you can taking 2 values, get a slope, and so this is the y end minus y end previous, a previous. This is, and we converge. So it will give us minus pi squared by 4. So let's see what we get. We get both eigenfunction, which is here. So my 2 values are this and this. Slope is 0.1 always. Slope is 0.1. But my endpoints are this and this, but we keep going closer and closer. I had to satisfy this y 2 is 0, and we get this. So my eigenvalue I get is minus 2.47. So accuracy is 0.001. Okay. So it converges in some 4-5 steps. Okay. If I can put more accuracy, I mean, I can put 3 zeros here or 4 zeros, and I get better and better result. Okay, but it will be more expensive. Okay, now this is in fact, is the first eigenvalue. I want the second eigenvalue, then what should I do? I should be closer to the second eigenvalue. You know, second method requires that you go, or any method, you need to be close to the root. So my two initial values are minus 11 and minus 8, and I just iterate it, I get to this, which is close to pi square, minus pi squared. Pi squared is roughly 10. Okay, so and that solution is this one. Okay, it works quite well. Okay, so eigenvalues are potentials. So this is Schrodinger equation for given potential Vx. Okay, non-dimensional Schrodinger equation. Y is the wave function. E is eigenvalue, energy eigenvalue. I do it for slightly complex problem. I'm not doing it for simple this one. So its potential is 1.1 minus x squared inverse. Okay. So I apply the exactly same method what I did, but you put Vx as well. So my potential is here. Okay, is divided by 100. Potential is really going to pretty large value at x equal to 0. It's like a square well potential, approximately. Okay, it is not quite the same square well, but it's like square well. Now we start with two initial guesswork here and this one. Okay, well, I guess this one, orange. And finally, we converge to this. Okay, and energy eigenvalue is 2.30. Second eigenvalue is 6.24, and the wave function is this. I demand that, of course, my put boundary condition that is 0 at both ends, okay, at -1 and 1. That's the boundary condition. We can solve potential values problems as well. Numerical problems, we can't do minus infinity to plus infinity. That's the thing, but in large box, you can work with. Okay. Now, remember my slope was arbitrary, so I chose any slope. So my wave function is not normalized, one which comes from the numerical computation. So how do we normalize it? We just take the computed value yx divided by the square root of -1 to 1, and this will normalize the slope, and then normalize the wave function. You can easily check y norm square integral dx. Okay, so it's easy to normalize, no problem. But what you get from computation is not guaranteed to be normalized. It's in general, it won't be normalized. Okay.